The photoelectric effect, as you know, was discovered in 1887 by, who is it? Hertz. It says that when light strikes a piece of metal, an electron is sometimes ejected. Not always, but sometimes ejected. Hertz tried to explain it using classical theory. Classical theory and quantum theory arises in that little mini assignment that you had, right? Hertz tried to explain it using classical theory. And Hertz said, using his classical theory, basically that electrons that were ejected needed energy to be ejected. And they get that energy from the light, from the EMR, from the electromagnetic radiation. And if the light had sufficient energy, then it would cause the electron to be ejected. If it didn't have sufficient energy, then it wouldn't cause an electron to be ejected. So if you wanted an electron to be ejected and the light that you were shining on it wasn't causing the electron to be ejected, then all you needed to do is get brighter light, because that's going to give you more energy, right? Need more energy, need brighter light. But the problem is that that prediction didn't match with the observations. So let's zoom forward a little bit to 1905. And who was it in 1905? Yep, Einstein. His photon theory. Einstein came along and said, hey, look, I got this theory, this photon theory that light's a particle. A wave, it's a wave, but it's also a particle. And the energy of that particle is equal to h times f. He says, and no one's really buying this. No one's really buying this photon theory. So he says, look, if I can explain this photoelectric effect, which has been around for almost 20 years, nobody's been able to explain it. If I can explain this photoelectric effect, and my photon theory matches all the observations that have been made for the photoelectric effect, will you finally kind of buy into photon theory? People are like, yeah, okay, whatever. And sure enough, his predictions that were made using photon theory matched up perfectly with the observations. So that kind of confirmed the existence of these photons, the existence of photon theory, the particle nature of light, right? Einstein said that because light exists as a particle and its energy is related to its frequency, then electromagnetic radiation below a certain frequency would never cause electrons to be ejected because it would never have enough energy. If energy is related to frequency, too low frequency, too low energy. Never going to cause the electrons to be ejected. What do you got to do if you want electrons to be ejected? Don't get more of the same thing. Don't get more of the useless photons that aren't causing anything. You got to get a different kind of photon, something more useful, something with a higher frequency and therefore a higher energy. Okay, once you have a high enough frequency, you get a high enough energy, and once you have a high enough energy, then the electron or electrons could be ejected. Now, what happens if you have a frequency that's way higher than it needs to be? You got a photon that's a little bit higher, an electron is ejected. What if you have a photon that's way higher than it needs to be? What's going to happen then? Yeah, it's going to release an electron still. Okay, same electron, except the electron's going to be more energetic because it has more energy to receive from that photon. And of course, if you have 50 photons that are above the threshold frequency, then you're going to have 50 electrons. If there are 50 way more energetic photons or higher frequency photons, you're going to have 50 way more energetic electrons that are ejected. We defined a couple of terms here, guys. We defined the threshold frequency. You can tell me what that is real quickly. Yeah. Good. Good. The lowest possible photon frequency that will cause an electron to be ejected. And that kind of corresponds to, but inversely corresponds to, the threshold wavelength. The threshold wavelength is a maximum possible wavelength as opposed to a minimum possible wavelength like threshold frequency is. What about work function? Yep.
If the energy that the photon would have to have for it to release.
Good. The minimum possible energy that you've got to have. The photon's got to have a certain frequency. Well, since frequency is related to energy, then it's got to have a certain energy as well. The work function is that minimum energy necessary. So let's write down an equation for that one. We've got the energy of a photon is HF is equal to hc over lambda. The work function is HF0 equals hc over lambda. Fill in the subscript. What is it? Right, lambda max. H times the minimum frequency, hc over the maximum wavelength. And then we talked about stopping potential. Talk a little bit more about that today. Anybody tell me generally what that is? That's the one that is kind of not really the photoelectric effect, really. We always talk about it in the context of the photoelectric effect, but really it happens. Yeah, really, it's after the photoelectric effect has happened, right? You've got an electron that's been ejected, and you're stopping that electron. So really, that's a way back to Unit 2 thing, the electricity unit. A charged particle is slowing down. It's like a car going up a hill. Okay, in the end, an electron that's been ejected, you may want to stop that electron via a potential difference in order to find the threshold frequency and the work function of the metal. And again, I'll show you how to do that today. That stopping potential is related to the kinetic energy of the electron that's been ejected. In fact, the kinetic energy of the electron that's been ejected, 1/2 mv max squared, ends up being converted to electric potential energy as that electron gets stopped. So we're going to say 1/2 mv squared equals qv stop. Now, both of those end up being equal to the initial kinetic energy of the electron as soon as it's been ejected. So we'll say Ek max is equal to 1/2 mv max squared equals qv stop. Finally, we had one more equation. We're going to put this one in red because it doesn't appear on our data sheet, and it comes from the law of conservation of energy. In other words, the energy that we start with is equal to the energy that we've got at the end, right? What kind of energy is it that we start with in this whole deal? Before the photoelectric effect takes place, what kind of energy do we have, John? Yeah, it's light energy. We're going to say that's equal to H times F. Or you could say it's equal to hc over lambda. Usually we'll say H times F. What kind of energy do we have after the electron has been ejected? William? It's kinetic energy. The electron has kinetic energy. But there was energy lost in the process, energy used up in the process of ejecting the electron. So what you end up with isn't quite equal to what you start with. What you end up with plus what you lost or used up in the process is equal to what you start with. What do we use up in the process? The work function. So we're going to say HF is equal to Ek max plus W. All of these equations you're going to use, this is the one, ironically, the one that doesn't appear on our data sheet, that you end up using probably the most often. It's the most complicated one because what you often have to do here is sub in things. Maybe HF gets replaced with hc over lambda, or Ek gets replaced with qv stop, or W gets replaced with H times F0. Generally, my rule of thumb is this. If within 5 or 10 seconds you're solving one of these problems and you don't know which equation to use, go to this one because it's the most complicated one. It's got the most possible combinations. Therefore, if you're having a little bit of trouble figuring out which one to use, it's probably going to be the one that's a little bit more complicated, right? All right, one final thing, and then we'll check over the work that we did yesterday here. Generally, we can use whichever value of Planck's constant that we want. We get two values, right? 6.63 times 10 to the minus 34 joules seconds, or 4.14 times 10 to the minus 15 electron volt seconds. Generally, we can use whichever one is convenient, whichever one we want. But there are two situations in which I must use the first one. I've got to use joules. I got no other option. Now remember, you can always use joules if you want. You never have to use electron volts. But there's two situations in which I have to use joules. Cassie, do you remember what one or both of those situations are? Good. Got to use joules for these two circled equations. Now, if you're just using kinetic energy like it appears in this equation, okay, without throwing in 1/2 mv squared or QV stop, you can still use electron volts. Okay, that's fair game. But as soon as you introduce either of those equations in the green circle, you've got to use joules, no other option. All right, 3 sets of work that you were, homework I'll call it, but you were working on them in class yesterday. 3 sets of questions on page 716, first of all. Was there any issues with those? We moved on to a couple more questions, but just before we move on even further, I want to find out if there's any issues with any of those questions. Good? No trouble? We have about 718. Number 2, yep. Number 2 says blue light of wavelength 410 nanometers. I'm going to say that's lambda. That is not lambda max. That's not a threshold wavelength or anything of the sort. Okay, if it says this wavelength barely causes electrons to be ejected, then that's a threshold wavelength, a maximum wavelength. Okay, if it says light below this wavelength causes electrons to be ejected, then that's a threshold wavelength. But if it just says, here's the wavelength of the light that strikes it, okay, that's not a threshold, a lambda max, that's just a lambda. That's the wavelength of the photon. The work function is 2.10 electron volts. I'm going to circle that electron volts as well, even though I may not have to convert. I'm going to convert it, or I'm going to circle it just in case. We want to find the energy of the emitted photon. The emitted electron, the photoelectron. The electron's going to have kinetic energy when it's released, right? So we're looking for EK max. You got lambda, you got W, you're looking for EK max. Which of these equations do you want to try? Which one do you want to try there, John? Let's try the red one. Okay, it looks a little bit tricky. Okay, having a little bit of trouble coming up with the equation that we want to use. So let's try the red one. HF is equal to EK max plus W. Don't panic. Don't worry at all about the fact that we don't have the value of F, because we can replace HF with HC over lambda, and we do have the value of lambda. We could also replace EK max with 1/2 mv squared, although we don't need to here because we're looking for EK. And we could also replace W with HF0 or HC over lambda max, but again, we don't need to because we have the value of W. We're in electron volts for work function now. Do we need to convert? Caitlin, do we need to convert that to joules? Could we convert it to joules? Sure, we can always convert to joules, but because we're not using 1/2 mv squared or QV stop, we don't need to convert to joules here. So I'm going to keep it in electron volts. If you're more comfortable using joules, then just use joules. You'll still get the same answer, except mine will be in joules. Sorry, mine will be in electron volts, yours will be in joules, that's all. Be careful to convert this correctly. 410 times 10 to the minus 9 meters. So what we're going to do there, Jazzy, is solve for this number on our calculators, of course. Take this number over by, yes, by subtracting. And when we do that, EK, I believe it actually worked out to be 0.929. Does anybody else get 0.929? Okay. I don't know where they got 0.932 from, but is that okay? We're good there, everyone else? Okay, the third set that you were working on yesterday was 719. Any issues with those questions on 719? They're good? Yep. Number 2, okay. 2 says you needed the work function from the table on that one. Does anybody have the work function for cesium? 2.1. Okay. So you don't need to obviously worry about remembering that number. Okay, that's going to be on probably buried in a page of information. Okay, but it'll be there somewhere in the question that you Yeah. So we're looking for the kinetic energy of the electron. We're looking for EK. This is lambda. Is it lambda max or just lambda? Because it's illuminated with 400 nanometer light. It's just lambda. If it says what's the kinetic energy of a photoelectron, blah, 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 when the electrons are just emitted by this light, then we would say it's lambda max. But it doesn't say that at all, right? It's emitted. Here's the wavelength, just going to be lambda. So we're going to probably say for this one, once again, HF is equal to EK max plus W, because it looks like it's a little bit more confusing with our variables here. Let's replace HF with HC over lambda. Looking for EK plus the work function. So real similar question to what we had actually in the last one, right? Let's use 4.14 because we have the electron volts. And we're not using 1 FMV squared or QV stop. And the work function, of course, is 2.1 electron volts. So let's get that number, and let's take that number over by subtracting. Good. And when we do that, do we get exactly 1.01 this time? Are they right this time?
Well, with round.
Okay. I don't know where that last one came from, that 0.932 that they had there. Did anybody figure out where that came from, that 0.932? Or maybe they just made a mistake. Good? All right, good. Have a look at this. I told you yesterday and today that I would give you a little bit more information on that whole stopping potential thing and why we might want to do that, how we would do that, and what kind of experiment would be performed in order to do that. Okay, in the end, you might want to stop an electron that's been ejected so that you can find the threshold frequency, so that you can find the work function, maybe even so you can do an experiment to find the value of Planck's constant. Okay, if you want to verify the value of Planck's constant. The experiment might be set up like this. You got a power supply, okay, which is basically a big battery that you can change the value of the potential difference. You got an ammeter, which measures the value of the electric current. So if there's an electric current, the little needle on the ammeter goes over here. Okay, if there's not an electric current, it goes down to 0. Now you've got inside this evacuated tube, no air, nothing to get in the way of things. Okay, glass tube, 2 electrodes. You've got a positive electrode, meaning the power supply must be set up like this, and then you get a negative electrode over here. You've got photons right here that are coming in and striking this metal surface, which is the negative electrode. Now, what happens? Assuming these photons are above the threshold frequency, then these electrons will be ejected. And they're going to be attracted over here towards this positive collector. Make sense? Now, because the battery or the power supply is set up the way that it is, you're not going to stop any electrons here. Okay, this is not a stopping potential issue right now. Okay, it will be in a minute. Okay, but right now it's just, look, the electrons are being ejected, and because of the way that the battery is set up, these electrons are going to end up going over to the collector and around the circuit. You're going to get a value on the reading of the ammeter. So it's going to read there's an electric current. Okay, good. Now what happens though? What happens if we switch things around? What happens if we switch the battery around so that this is the negative collector and this is the positive terminal? Our photons are still above the threshold frequency. Okay, so our photons will still cause the electrons to be ejected. The electrons are going to go off like this. But this time, instead of being attracted to that other collector, this time they're going to be repelled. If we have a high enough potential difference, then we can stop these electrons dead in their tracks. We can measure the potential difference at which we stop these electrons. How do we know the electrons have been stopped? How do we know the electrons are going to be stopped here? We can't see them. We're going to measure no electric current in the ammeter. The needle of the ammeter is going to go down to 0. So that's how we know the electrons have been stopped. Once the ammeter reads 0, we measure the potential difference across the power supply that caused that, and we record that. We record that as V stop. Now, what else do we record? Okay, you've got to always record two variables. What was the frequency of the light? The frequency of the photons that struck this photo-emitting surface, this electron-emitting surface, and then the stopping potential that was required to stop those electrons. Then what would we do? Well, we would probably increase the frequency. And what would we do as a result of that? We'd measure whatever stopping potential was required to stop those. We'd adjust the power supply again to stop the electrons, to get a 0 reading on the ammeter, and we would see what value that was. Make sense? Now, at that point, you'd have a couple of options. Okay, what you'd usually do, let's say we got a table here, a frequency versus V stop. What we'd usually do is create another table, an analysis table, F versus EK max. Now, EK max could be easily found. That column could be easily found just by saying Q times the stopping potential. Now, at this point, you'd plot a graph. You could have plotted a graph right here, F versus stopping potential. But usually the graph that you see would be this graph, kinetic energy max versus frequency. Now, what's kind of neat about, I don't know about neat, but unique about both of these graphs is that although they're both straight line graphs, both of them will look like this. Both of them will have both an x-intercept and a y-intercept. Now, there's a couple of things that we can find from these graphs. So we're going to focus on this one here, okay? A couple of things that we can find from these graphs. We can find the value of Planck's constant. We can find the value of the threshold frequency. And we can find the value of the work function. Now, here's how we're going to do it. Just create a little bit more space here. We're going to go through a procedure that you guys have gone through several times before, at least a half a dozen times this year so far. This is a straight line graph, right? What do you do when you have a straight line graph? You guys know where to start with this, right, Brad? What is it? Right, the equation from the graph. The equation from the graph will be y is equal to mx plus b. Now, the y-axis is ek. M is the slope. The x-axis is frequency. There is clearly a y-intercept here, right? Okay. I don't know what it is, but okay, we can't get rid of the y-intercept. Now, you got to come up with an equation from your data sheet, or in this case, it's not actually on your data sheet. What's the equation that we've done that has both ek and f in it? About hf is equal to ek max plus the work function. Let's rearrange that to take the same form as the equation from my graph. Let's say ek is equal to hf minus w. On this graph, we can cancel out ek because it appears in both. We can also cancel out f because it appears in both. On this graph, the slope would be equal to what? Yep, Planck's constant. The slope is equal to Planck's constant. If you get a graph like this and you want to find Planck's constant, then just take the slope of that graph. And finally, the y-intercept, b, would be equal to what? Yep. The negative of the work function. So if we took the absolute value of the y-intercept, it would be equal to the work function. Now, I told you there's three things you could find from this. Planck's constant, the work function, but I told you could also find the threshold frequency. Anybody want to take a stab at how I might find the threshold frequency? We're going to have to just reason through this. You can't really do an analysis with the equation for this, but just reasoning. It's going to be the x-intercept. Look at this. The frequency at which electrons start having kinetic energy. The frequency at which electrons start being ejected, right? That's the threshold frequency. Now, the reason I went through this graph is because we see this often, this EK versus frequency graph. We see it often. You will get, I've told you this a dozen times before, you'll get a question on your exam that is a graph. It may be this, okay, although there's a very good chance it won't be this graph. But because we see this relatively often, there's also a decent chance that it might be this graph. Less than 50%, but probably more than some of the other graphs that we could see. You could also see some other graph that you've never seen before in your life. Okay, there's probably a pretty good chance you will see one that you've never seen before in your life. The more we go through this kind of analysis, the better able we're to deal with, questions involving graphs that you've never seen before. Okay, does that make sense? What I've just done there? Okay, we've done that quite a few times now, right? Including on a number of our, I think on all of the labs that we've done actually. Okay, you see this graph for the first time today. If you saw this graph for the first time on June 25th, there's no reason to panic. Okay, we know how to deal with this. If you see another graph that you've never seen before on June 25th, there's no reason to panic. Just do this. I'm even suggesting to you that although this graph, is relatively common, don't memorize what I've just squared off in red there. Just understand how to figure it out every time, whether it's for this or any other graph. Does that make sense?